So I completed the first rings section in Gallian, section 12. And so I am, this is October 2nd when I'm making this video, and I finally crossed the 50% mark. I'm at 192 problems out of 1,688. And so that means that I've attempted 463 proofs, and there are 37 proofs in this particular update. Yeah. And so that will just keep going down this way. All right, so then to the book. As I showed in the last section, I talked about the what's mentioned in this section about rings. I've gotten to use in the problems the characteristics of a ring for subrings. Then, of course, just more. I think just more. Subrings, of course, it's itself a ring with the operations of R. And so in this case, this is really almost all of these problems. A lot of these calculations have been the multiplicative tables for integers, for various integers mod n, and sometimes primes. Yeah, a simple proof, just a simple proof. I got it correct. Then the intersection of any collection of subrings is also a subring. I think I did it correct. I looked at the answer and it looked like what I did. Then going through the examples and proving all the examples are subrings. So just go through. I did it in a very tedious way, I think, going through all the properties, but I like doing it that way. And so they all worked out. Just go through, you know, a plus b equals b plus a plus b plus c grouped differently. Is there a zero? Is there an inverse? Then the ABC, and then the transitive properties, and you're done. Yeah, just do that repeatedly. Yeah, I did not do this correctly, really. I mean, when I read, there's a much neater way that the book shows to do it. Yeah, I think this worked out fine. These all were various proofs of rearranging what you multiply the element by in a ring. Yeah, let R be a ring. The center of R is a set. This is the center of a ring is a subring. That's what I'm supposed to prove. Just go through all the properties. Back to the identity, what it does. Yep, and when they asked what are the units of the algebraic numbers, right? That's what they are. I immediately was like, yeah, I know it's 1 plus 1, I minus I. Yeah, and that was correct. Yeah, same for the polynomials with integer coefficients, plus 1, minus 1. I think the real ones is plus or minus a, where a is a real number, but I'm not sure. And I don't have the answer for it, so I do not know. Yeah, the unit divides every element of the ring. Just work it out. Then some calculations. Yeah, the book had a much clever way of saying, you know, for a commutative ring with unity, if a is a unit and b squared is equal to 0, then a plus b is also a unit. I think I did it correctly, but I really liked the way the answer was done. And then just calculating a few integer rings, mod, numbers mod, either the square of a prime, 3 square, or I know one that's got 0 divisors from Mendelssohn, Z4, then a prime, and then 6, which is composite, just as example, just to get a feel for it. And then do the proof for 30 after looking at the examples, just getting into it. That's what I did with these calculations. And I continue to do that later as well. Yeah, right, I got this right. A to the fourth is equal to a squared, then a to n is equal to a squared. And it's just, you just keep repeatedly applying a to the fourth a squared, and you will always end up back to a squared no matter how many of them you have. Yeah, I think I got that right, even though I do not have the answer for this problem. Yeah, this one, I don't feel like I did it the right way. I tried to use my number theory knowledge. And then in the case of 35, 35 is really, there is no integer n greater than 1 such that a to the n equals a for all a and z sub m if m is divisible by the square of some prime. And the answer there is because you're going to wind up getting a bunch of zero divisors. That's really what that is all about. And you don't get any divisors for zero divisors for primes, and also often for composites. As long the moment there's a power of a prime in there, you're going to get zero divisors. And that's what that proof is about. But I wanted to do a bunch of examples just to get into it. Yeah, here I said everything and I thought it was obvious, but really what the book had was close under multiplication. That's what I thought I was explaining here, as well as other things, but I didn't. Then this problem, I think I'm right. So is Z6 a subring of Z12? Well, it is a subgroup, but I don't believe it's a subring because the operations are different. That's what I believe, even though Z6 is a ring, but it's about the operations of R. Somebody, if you know the answer, but I think it is not. At first I had yes, but I was like, no, when I look at the tables, I don't see a subring in here. Maybe I'm wrong, but I think I'm correct. 39, I just did some exploration, then wrote it out. Yeah, in detail, it was fine. Just make sure that all the properties are satisfied for a subring. These three were really easy, it turns out. I thought there was a trick, but there really wasn't. They all work out. And sure enough, all these matrices are subrings of m sub 2z. Then this one, I did the properties for a ring, but I forgot something really obvious, which is I forgot to check if you multiply two of the elements, do you still stay within? And you don't. You don't. So it's not closed. That's lesson for the future. I missed that when you multiply two elements, you leave the subring. More manipulations to show all the properties of a subring are a ring in the operation of the ring. And then in the case of 47, I knew where I was going and I started adding them, but I didn't put the m. I knew it was 1 over 2 to the n, but I even have it here, but really it's m. I should have made it a constant, and I did not do that. So I was close. And I think I got 48 correct, which is just a variation of that one, of 47. Yeah, more proofs, small proofs. Yeah, and then 53, I was like, the way I read this logic, are you sure that you only need one of the two to be zero for it to be a zero divisor? And I even wrote it up, and I can't believe that I did, because this is completely wrong. It's got to be 0, 0. But I don't understand the logic of the question. And so I just went and took Z4 times C4, and I did the multiplication table, the whole thing. And then I wrote out what I think is the logic. And I wish if this problem had been written like this, I would have understood it better, and I wouldn't have gotten wrapped around the axle about something that was completely wrong. My mistake, totally my mistake. But definitely, if I had started with considering A, B, C, and D, not just A and B, this nifty logic wouldn't have thrown me for a curve, for a spin. And so when I do it the long way, I get it. So really, you're multiplying A, B, and C, D to get 0, 0, and that's how you get a zero divisor. But if you don't have any zero divisors, if A and D are 0, or A and B are 0, or C and D are 0, or B and C are 0. All these combinations give you a 0 divisor. And then if you get a 0 divisor by multiplying A and C or B and D, then you also get a 0 divisor. That's really what this problem is about, in my opinion. 55, I thought I had it, but no. I said every non-zero element of R is a unit of R. It is not. That's wrong. And so the way the book laid it out is better, and I'm learning about it. So R is a commutative ring with more than one element. Then if of every non-zero element A of R, we have AR equals R, then R has a unity and every non-zero element has an inverse. I thought I was good by making every non-zero element a unit that I would solve that problem. That is not correct. It has to be done by including another element, an element X that is not 0, to make it all work. And then 56, I'm asked for an example where A to the n is equal to B to the n, A to the m is equal to B to the m, and n and m are what do you call it, GCD is equal to 1. And sure enough, I had already done, I went back to my calculations. And right here, they're right here. You just read these off. The elements are different, the powers are the same, and the result is the same. And then an easy proof that I think I sort of did correct, but I should have just taken it to the side to 0 and do this. This is a lot more straightforward. Yeah. Yeah, and yeah. Right. Okay, that's it.